Apart from the nature of the waves and their wavelength, how does the process of the image produced by X-rays differ from that produced by an ultrasonic scan? This question's come up a couple of times. So an ultrasonic scan uses reflection of waves to produce an image, whereas X-ray photograph uses a shadow if I just draw something like that, if this is a part of the body, I don't know, I'll draw a bone here actually. There's a bone. Okay, when the X-rays come down past that, what they do is underneath it, they blacken all around, apart from this bit here. Hope you're not laughing right now at my drawing, but the X-rays all around here are blackening the film, and they're really leaving a shadow, and the shadow's a bone there. Oh, can't see the drawing, so you weren't laughing. Okay, there's the bone, there's the shadow, and there's the blackened X-ray film. And that's the end of that question, and that was 2005. Right, this is the last question you had in your your medical imaging handout sheet, and this is 2007. CT and, sorry, it's maybe not the last question. And there's another one. Okay, second last question. This is 2007. CT and MRI are powerful diagnostic tools which use computers to produce detailed images of the body. Both techniques require electromagnetic radiation in order to operate. Name the region of the electromagnetic spectrum used in CT scans. So CT scans, of course, use X-rays. Use the name of the region of the electromagnetic spectrum used in MRI scans. So MRI scans, of course, use a huge magnet, and that's not part of the electromagnetic spectrum. So what they do is they use a huge magnet to create a magnetic field across the hydrogen atoms in the body, and then they apply a radio frequency. So in other words, it's radio waves, and that causes the hydrogen atoms in the body to resonate. Describe briefly the role played by the electromagnetic radiation in the resonance process of MRI. So I've kind of talked over myself there, but we'll go back on that again. So radio waves applied at the natural frequency of the hydrogen atoms in the body, or nuclei in the body. I might write nuclei, it's probably a better thing to write there. And that causes resonance. And then the maximum energy at resonance is absorbed by the hydrogen nuclei, and that causes them to, and we'd use this word in your notes, precess. Okay, that's your 2 marks. In ultrasonic imaging, a piezoelectric crystal is used both to generate and detect ultrasonic waves. Describe briefly how ultrasonic waves are generated using the piezoelectric effect. So you have an alternating frequency applied to the crystal. And again, that's at its natural frequency. And so it resonates. And then when it resonates, it gives out ultrasonic waves. Okay. So it causes it to change, the crystal changes shape and produces a sound or a vibration. Part 2. Figure 5.1 shows a printout from an ultrasonic A scan from the investigation of a patient's eye. So if you remember, the A scan is a depth measurement, gives you a measurement of depth. So it shows you the initial spike, the front lens surface, the back lens surface, the retina, the sclera and the orbital fat. Ultrasonic velocity in the lens is 1641 meters per second. Use the data from the A scan and associated information above to calculate the thickness of the eye lens. So if you think about what's happening there, you've got sound hitting here and being reflected back, and you can see where that is, and that's at B. But then the sound also then travels on through, if I do that in red, and out again. And you are getting an echo from that too. But it's travelled, and the extra distance that it's travelled is double the depth of the lens, if you can see that, into the lens and out again. So if we have a wee look here, we can see here that there's the front lens surface, and then this is the back lens surface. Okay, so that is the echo from the back surface of the lens. That's the time when it hits, or whenever it's received. And so the difference in time between those two is the time it takes to get to the back and out again. And so that's double really time. This is like a typical echo question you would have done in GCSE. So first of all, we'll work out the time for it to echo. So the time for the echo is equal to, if we have a look at this, it's 8 microseconds, and then it went in there at 1, 2, 3 microseconds, so it's 8 minus 3, and that gives you 5 microseconds. And so that's the echo time. So the time for the thickness of the lens is 5/2. It takes to travel the thickness of the lens. So this just becomes a speed is distance over time question. And we're looking for the distance, so distance is speed by time, and that's equal to 1641 multiplied by 5/2, and it's microseconds. That's very important, of course, by 10 to the minus 6, and that gives you a depth of 4.1 by 10 to the minus 3 meters, or 4.1 millimeters there. And of course you can't see that, so there's the calculation again. Speed is distance over time, distance is speed by time. 1641 multiplied by that time just taken to travel the thickness of the lens is the 5 divided by 2, gives you 4.1. And that's the end of 2007.